The vastness of space has always captivated the human imagination. From the earliest astronomers charting the movement of stars to dreamers imagining voyages beyond our planet, the cosmos represented both mystery and possibility. In the mid-20th century, these dreams converged with geopolitics, technological innovation, and the ambitions of superpowers, giving rise to a historic competition that would redefine humanity's understanding of the universe. This was the era of the space race, a period when rockets, satellites, and astronauts became instruments not only of exploration, but also of national pride and ideological supremacy. Hello, and welcome to the Other Side Stories. Here, we travel beyond the usual headlines to explore the untold tales of world history, mysteries, turning points, and hidden connections that shaped our planet. If you love discovering how the past still echoes in our present, you're in the right place. Let's uncover the other side of history together. The story of the space race begins in the shadow of World War II. The devastation of the conflict left nations not only rebuilding their economies and societies, but also advancing their technological capacities. Among these advancements, rocketry emerged as both a symbol and a tool of power. German engineers, notably Wernher von Braun, had developed the V-2 rocket, a weapon that, despite its destructive role during the war, demonstrated the potential of rockets to transcend the boundaries of Earth itself. When the war ended, the Allies, recognizing the strategic value of these scientists and their knowledge, recruited many of them, setting the stage for a post-war contest of technological supremacy. By the late 1940s, the world had effectively divided into two major ideological blocs: the capitalist West, led by the United States, and the communist East, dominated by the Soviet Union. The Cold War that emerged was fought not only in conventional military terms, but also through propaganda, economic influence, and scientific achievement. Space exploration became one of the most visible and symbolic arenas of this contest, where every satellite, rocket launch, and eventual human voyage would be scrutinized as evidence of national capability and technological prowess. In the immediate post-war years, both superpowers explored ballistic missile technology. The United States established research centers such as the Redstone Arsenal in Alabama, where German engineers contributed to the development of American rockets. Simultaneously, the Soviet Union, under the direction of Sergei Korolev, advanced its own missile programs, drawing on captured German technology and domestic expertise. By the early 1950s, both nations had demonstrated medium-range and intercontinental missile capabilities, signaling the beginning of what would later be termed the arms race. But beyond missiles, the eyes of leaders and the public alike began turning toward the stars. The launch of the Soviet satellite Sputnik 1 in October 1957 marked a seminal moment in this emerging competition. No larger than a beach ball and weighing just over 180 pounds, Sputnik circled the Earth every 96 minutes, transmitting a simple beep that could be detected by radio operators worldwide. Yet this small satellite sent shockwaves far beyond the scientific community. For Americans, Sputnik symbolized a perceived technological gap and ignited fears about Soviet superiority in both military and scientific domains. The event catalyzed the creation of new institutions, including NASA, the National Aeronautics and Space Administration, in 1958, with a mission to coordinate and accelerate American space efforts. Sputnik's success also spurred the global public imagination. Suddenly, the possibility of human presence in space seemed tangible rather than fantastical. Schools introduced new curricula emphasizing mathematics and science, hoping to cultivate a generation capable of meeting the challenges of the space frontier. Governments increased funding for research in physics, engineering, and computer science. And in the halls of the United Nations and across media outlets, space exploration became intertwined with narratives of national pride, political ideology, and the destiny of humanity itself. The Soviet Union, buoyed by this early triumph, pressed forward with ambitious programs. Following Sputnik, they launched Sputnik 2 in November 1957, carrying Laika, a dog who became the first living creature to orbit the Earth. While Laika's journey was tragic, it demonstrated the feasibility of sending living beings into space and returning data about biological responses to weightlessness and radiation. The achievement reinforced the Soviet position as a leader in space exploration and deepened American urgency to respond. In the United States, early satellite projects such as Explorer-1 sought to catch up. Launched in January 1958, Explorer-1 not only placed the U.S. into orbit, but also discovered the Van Allen radiation belts, a region of charged particles surrounding the Earth. Scientific accomplishment and national symbolism intersected powerfully, as every technical milestone was portrayed as proof of ingenuity, perseverance, and ideological legitimacy. The space race was thus not merely about hardware. It was about demonstrating a nation's capacity to innovate, to inspire, and to command the future. Throughout the early 1960s, the competition intensified. The Soviets achieved numerous firsts: the first human in space, Yuri Gagarin, in April 1961, and the first woman, Valentina Tereshkova, in 1963. Each mission was broadcast worldwide, magnifying the symbolic impact of Soviet achievement. For the United States, these milestones served as both warning and motivation. President John F. Kennedy's famous speech before Congress in 1961 committed the nation to landing a man on the moon and returning him by the end of the decade, a pledge that would galvanize resources, talent, and public imagination. Achieving a lunar landing required innovations across multiple fields. Propulsion systems, navigation technology, life support, spacecraft design, and mission planning had to converge seamlessly. NASA developed the Saturn V rocket, a behemoth capable of propelling astronauts beyond Earth orbit. The Apollo program became a massive organizational undertaking, involving thousands of scientists, engineers, technicians, and support personnel. The meticulous preparation, rigorous testing, and iterative problem-solving exemplified the immense scale and complexity of human space exploration. Meanwhile, the Soviet Union continued to pursue parallel goals. Cosmonauts such as Alexei Leonov conducted the first spacewalks, and the Soviets developed space stations to sustain long-duration missions. Yet, despite early successes, internal challenges, technological limitations, and strategic decisions meant that the Soviets would ultimately concede the moon landing race. Nevertheless, their contributions to orbital mechanics, spacecraft design, and human spaceflight laid foundational knowledge for the broader international space community. The space race also had profound cultural implications. Popular media, films, television, literature, and art grappled with themes of space travel, alien worlds, and the ethical dimensions of exploration. Children dreamed of becoming astronauts, engineers, or scientists, inspired by stories of bravery, curiosity, and adventure. Governments leveraged media and education to cultivate both national pride and scientific literacy. Space, once the domain of distant speculation, became an integral part of collective imagination, shaping perceptions of possibility and the human spirit. Beyond the geopolitical and cultural dimensions, the space race generated enduring scientific knowledge. Satellite observations advanced meteorology, communications, and earth sciences. Human missions provided data on physiology, psychology, and the effects of microgravity. Technologies developed for space exploration, computing systems, material science, robotics, found applications across medicine, industry, and daily life. The pursuit of the heavens catalyzed innovation on Earth, demonstrating how competition can drive creativity and technological progress. Yet, the space race was not solely defined by triumphs. Failures, accidents, and tragedies reminded participants and observers of the risks inherent in venturing beyond Earth. Launch failures, technical malfunctions, and human error occasionally resulted in loss of life. These setbacks, however, became lessons for refinement, reinforcing the importance of planning, redundancy, and rigorous testing. The narrative of space exploration thus intertwined ambition with caution, hope with realism, and audacity with humility. By the late 1960s, the focus had shifted decisively toward the moon. Apollo missions tested systems in increasingly complex scenarios, culminating in Apollo 11. On July 20, 1969, Neil Armstrong and Buzz Aldrin set foot on the lunar surface, while Michael Collins orbited above. The images of the astronauts, the footprints, and the American flag, transmitted to millions of viewers worldwide, symbolized the zenith of the space race, an event where technological mastery, human courage, and national pride coalesced. Armstrong's words, "That's one small step for man, one giant leap for mankind," encapsulating both achievement and the shared human aspiration to explore. The lunar landing had ramifications beyond the United States. It demonstrated that ambitious national programs could achieve seemingly impossible goals, inspiring other countries to invest in space programs. It also signaled a transition in the space. As the 1970s dawned, the world began to recognize that the space race had evolved beyond the initial contest of firsts. While the moon landing symbolized a pinnacle achievement, the broader objectives of space exploration, including sustained presence in orbit, scientific experimentation, and interplanetary observation, became increasingly important. Apollo missions continued, providing opportunities to test longer-duration flights, complex navigation, and advanced lunar science. Each mission contributed invaluable data, from geologic samples that revealed the moon's formation history to observations of the Earth from orbit that deepened our understanding of planetary systems. During this period, both superpowers began exploring the concept of space stations as platforms for continuous human presence beyond Earth. The Soviet Union launched the Salyut series, beginning in 1971, pioneering orbital living and scientific experimentation. These early stations were modest in scale, but monumental in ambition, demonstrating the feasibility of prolonged human habitation in microgravity. American efforts, including Skylab, offered similar opportunities, testing life support systems, crew rotation schedules, and the impacts of long-term exposure to space on human physiology. The data collected not only informed future missions, but also laid the foundation for the eventual creation of the International Space Station decades later. Scientific collaboration, though still framed by geopolitical rivalry, began to emerge. Shared observations of cosmic phenomena, satellite telemetry, and comparative studies of human adaptation highlighted the universal nature of scientific inquiry. Researchers in both the United States and the Soviet Union published findings in peer-reviewed journals, advancing global knowledge even amid political tensions. The space race thus became a conduit for both competition and the cross-pollination of ideas, illustrating that the pursuit of knowledge can transcend ideological boundaries. Planetary exploration also took center stage. Robotic probes such as Mariner, Venera, and Luna provided insights into Mars, Venus, and the Moon's far side. These unmanned missions allowed scientists to study atmospheres, surface composition, and gravitational fields, paving the way for future human exploration. The ability to collect and transmit data across millions of kilometers required innovations in communication, navigation, and autonomous control, technologies that would later support more sophisticated missions and civilian applications, including satellite communications, weather forecasting, and Earth observation. Public engagement remained a crucial aspect of the space race's legacy. Televised launches, live broadcasts of astronaut activities, and educational programs captured the imagination of millions. Children around the globe aspired to careers in science and engineering, motivated by the daring and dedication of astronauts. Science fiction literature and cinema, inspired by real-world developments, further fueled cultural fascination with space, exploring speculative concepts such as interstellar travel, extraterrestrial life, and the ethical implications of exploring new worlds. The interplay between real achievements and cultural representation amplified the space race's impact beyond technology and politics. The psychological dimension of space exploration emerged as an area of increasing focus. Researchers studied the effects of confinement, isolation, and stress on astronauts, recognizing that mental resilience was as critical as physical fitness. Training programs included simulations of extended orbital missions, emergency procedures, and problem-solving under pressure. These studies informed not only space programs, but also broader understandings of human behavior in extreme environments, influencing fields ranging from military operations to polar expeditions. Meanwhile, diplomatic efforts in space began to take shape. By the mid-1970s, the notion of détente, a relaxation of tensions between the superpowers, translated into cooperative initiatives in orbit. The Apollo-Soyuz test project in 1975 marked the first joint U.S.-Soviet space mission, in which American and Soviet spacecraft docked in orbit and astronauts conducted joint experiments. This symbolic and technical collaboration signaled a recognition that space exploration could serve as a bridge between nations, fostering trust, exchange of expertise, and shared achievement. It set a precedent for future multinational programs and illustrated the potential of science as a unifying force. Technological spin-offs from the space race began permeating civilian life. Miniaturization of electronics, advances in computing, and development of sophisticated materials originally intended for spacecraft found applications in consumer products, medical devices, and industrial processes. Satellite technologies enabled global communications, weather monitoring, and navigation systems, fundamentally altering society. The investment in space infrastructure, while initially motivated by competition, yielded long-term benefits for humanity, demonstrating the unforeseen advantages of ambitious scientific endeavors. The 1980s and 1990s saw the space race transition from direct superpower rivalry to a more diverse and international endeavor. European nations, Japan, and other countries developed independent programs, contributing satellites, research stations, and exploration missions. The U.S. Space Shuttle program introduced reusable spacecraft, allowing more frequent access to low Earth orbit and enabling construction of modular space stations. Soviet and later Russian programs continued with Mir, a symbol of human ingenuity and perseverance. Collaborative projects like the Hubble Space Telescope expanded humanity's observational reach, revealing galaxies, nebula, and phenomena previously unseen, inspiring awe and curiosity across generations. Science continued to benefit from the competitive spirit initiated by the space race. Robotic missions such as Voyager provided unprecedented data about the outer planets, including Jupiter, Saturn, Uranus, and Neptune. These missions tested engineering limits and expanded scientific understanding of planetary systems, magnetic fields, and celestial mechanics. The data also fueled theoretical models, informing astronomers about the formation of planets, the behavior of atmospheres, and the dynamics of moons and rings. Each advancement reflected the cumulative effect of decades of focused effort, resources, and ambition that the space race had catalyzed. Education and workforce development were enduring legacies. Space programs inspired generations to pursue careers in STEM fields, leading to innovations not only in aerospace, but across engineering, computing, medicine, and environmental sciences. University programs expanded, research funding increased, and international exchanges facilitated the transfer of knowledge. The space race's impact on human capital, though less visible than rockets or satellites, contributed to sustained technological growth and global scientific literacy. The narrative of space exploration also raised philosophical and ethical questions. As humans ventured beyond Earth, questions emerged regarding the responsibility to preserve extraterrestrial environment, the ethics of potential contact with life beyond our planet, and the equitable access to space-based resources. Debates about militarization, commercial exploitation, and international governance reflected the broader challenges of balancing ambition, security, and stewardship. The foundations laid during the space race informed policy, treaties, and frameworks that continue to guide human activity in space today. Furthermore, the space race fostered a sense of global perspective. Images of Earth from orbit, particularly the Earthrise photograph taken during Apollo 8, highlighted the planet's fragility and unity. This perspective influenced environmental movements, international cooperation, and a recognition of shared responsibility for planetary stewardship. Space exploration, while initially a tool of competition, became a catalyst for a broader understanding of humanity's place in the cosmos. Scientific collaboration continued to flourish as nations recognized the practical and symbolic value of joint missions. Projects such as the International Space Station, initiated in the 1990s and realized in subsequent decades, embodied the transition from rivalry to partnership. Multinational crews, shared research, and joint funding illustrated that space exploration could unite countries around common objectives, demonstrating the potential of science as a unifying force. Technological spin-offs from the space race began permeating civilian life. Miniaturization of electronics, advances in computing, and development of sophisticated materials originally intended for spacecraft found applications in consumer products, medical devices, and industrial processes. Satellite technologies enabled global communications, weather monitoring, and navigation systems, fundamentally altering society. The investment in space infrastructure, while initially motivated by competition, yielded long-term benefits for humanity, demonstrating the unforeseen advantages of ambitious scientific endeavors. The 1980s and 1990s saw the space race transition from direct superpower rivalry to a more diverse and international endeavor. European nations, Japan, and other countries developed independent programs, contributing satellites, research stations, and exploration missions. The U.S. Space Shuttle program introduced reusable spacecraft, allowing more frequent access to low Earth orbit and enabling construction of modular space stations. Soviet and later Russian programs continued with Mir, a symbol of human ingenuity and perseverance. Collaborative projects like the Hubble Space Telescope expanded humanity's observational reach, revealing galaxies, nebula, and phenomena previously unseen, inspiring awe and curiosity across generations. Science continued to benefit from the competitive spirit initiated by the space race. Robotic missions, such as Voyager, provided unprecedented data about the outer planets, including Jupiter, Saturn, Uranus, and Neptune. These missions tested engineering limits and expanded scientific understanding of planetary systems, magnetic fields, and celestial mechanics. The data also fueled theoretical models, informing astronomers about the formation of planets, the behavior of atmospheres. As the decades progressed, the focus of space exploration expanded beyond Earth orbit and lunar missions toward the broader solar system. The early robotic missions that had charted the moon's surface evolved into ambitious programs targeting planets such as Mars, Venus, and Jupiter. Unmanned probes like the Mariner and Viking missions offered unprecedented insight into planetary atmospheres, surface geology, and potential habitability. Mars, in particular, captured the imagination of scientists and the public alike. Its deserts, canyons, and polar ice caps prompted questions about the possibility of past or present life, and missions were carefully designed to study the planet's climate, geology, and chemistry. These robotic pioneers demonstrated that even in the absence of humans, exploration could yield transformative knowledge. Technological innovation continued to accelerate as space programs matured. Robotics, telemetry, and remote sensing became critical tools for planetary science. Instruments capable of analyzing soil composition, measuring radiation, and imaging surfaces in multiple wavelengths allowed scientists to construct detailed maps and models of celestial bodies. Innovations in computing and data processing enabled the handling of vast quantities of information sent from deep space probes, allowing researchers to simulate conditions and plan future missions with precision. These capabilities, forged in the crucible of the space race, laid the groundwork for the era of interplanetary exploration. At the same time, attention returned to the challenges of sustaining human life in space. Space stations, both Soviet and American, served as laboratories for understanding the effects of prolonged exposure to microgravity, cosmic radiation, and isolation. Astronauts conducted experiments in biology, medicine, material science, and physics, generating data essential for the planning of long-duration missions. The psychological and physiological studies undertaken in orbit revealed the complex interplay between human biology and space environments, highlighting the necessity of meticulous preparation, exercise regimens, and adaptive technology for future explorers. The 1980s also saw the increasing involvement of private industry in space. While initially driven by government programs, the development of commercial satellites, launch services, and specialized spacecraft introduced a new dimension to space activities. Telecommunications companies deployed satellites that enabled global broadcasting, mobile communication, and data transmission. These commercial ventures demonstrated that space exploration and utilization could be profitable, providing incentives for technological innovation and operational efficiency. In many ways, the private sector's engagement signaled a shift from pure competition to collaboration between public and private entities in advancing humanity's reach beyond Earth. Despite these advances, challenges remained. The technical complexity of spaceflight, the high costs, and the inherent risks meant that every mission required rigorous planning, testing, and redundancy. Accidents, such as the Space Shuttle Challenger disaster in 1986, underscored the perils involved and reminded the world that even with advanced technology, human lives remained vulnerable. These tragedies prompted reviews, reforms, and the implementation of more stringent safety protocols, reflecting the sobering realities of operating in the unforgiving environment of space. International collaboration gradually became the dominant paradigm in space exploration. By the 1990s, joint projects between former rivals and new partners alike emphasized the shared benefits of scientific discovery. Multinational crews conducted experiments aboard space stations, coordinated satellite deployments, and developed infrastructure for planetary exploration. This cooperative approach not only expanded knowledge, but also fostered diplomatic goodwill, demonstrating that space could serve as a bridge between nations even after decades of rivalry. The exploration of Mars gained particular prominence during this era. Robotic landers and orbiters collected data that helped scientists understand the planet's geological history, atmospheric composition, and potential for supporting life. Discoveries of ancient riverbeds, mineral deposits, and seasonal changes inspired new hypotheses about the planet's habitability. Each mission built upon the previous, forming a cumulative record of knowledge that guided planning for potential human missions. These efforts reflect the enduring influence of the original space race, in which competition spurred the rapid development of capabilities that would now support exploration beyond the Moon. Advances in propulsion technology also opened new possibilities. Ion engines, high-efficiency chemical rockets, and experimental propulsion systems allowed for longer-duration missions with reduced fuel requirements. These innovations not only enabled exploration of distant planets, but also reduced costs and increased mission flexibility. Combined with improvements in navigation, communication, and autonomous control, these developments made it feasible to consider missions to asteroids, comets, and beyond, expanding humanity's reach within the solar system. Scientific outcomes from the space race and subsequent missions had profound implications for understanding Earth itself. Satellite observations provided insights into climate patterns, ocean currents, atmospheric dynamics, and environmental changes. Earth observation satellites became essential tools for monitoring natural disasters, managing resources, and studying ecological systems. The technological advances driven by space competition thus had direct applications for managing life on our home planet, illustrating the interconnectedness of exploration and sustainability. The cultural impact of space exploration persisted throughout this period. Media coverage, documentaries, and literature continued to shape public perceptions of space, celebrating human ingenuity while exploring the philosophical dimensions of exploration. Questions about the meaning of human presence in the cosmos, our responsibilities as stewards of planetary environments, and the potential for life beyond Earth became central themes in scientific discourse and popular culture alike. Space exploration inspired education, imagination, and ethical reflection, extending the influence of the space race far beyond its initial geopolitical context. By the turn of the 21st century, the legacy of the space race had fully integrated into global scientific, technological, and cultural frameworks. The foundations laid by decades of competition enabled collaborative initiatives, international partnerships, and ambitious projects such as the International Space Station. Nations that were not part of the original superpower rivalry developed capabilities in satellite technology, remote sensing, and planetary exploration, contributing to a more diverse and inclusive era of space activity. The initial rivalry that defined the mid-20th century had transformed into a complex ecosystem of exploration, innovation, and knowledge sharing. Emerging technologies, including robotics, artificial intelligence, and advanced materials, continued to expand possibilities. Unmanned missions to distant planets, asteroids, and comets provided unprecedented data, while telescopes like the Hubble Space Telescope offered glimpses into the furthest reaches of the universe. These achievements were made possible by the infrastructure, expertise, and institutional knowledge developed during the intense period of the space race. In many ways, the competition that had begun as a geopolitical struggle evolved into a long-term driver of human advancement and cosmic understanding. Commercial space ventures accelerated in the 21st century, building upon the foundations of government-led programs. Private companies developed reusable launch systems, cargo missions to orbit, and prospective crewed missions beyond Earth. These initiatives introduced competition, innovation, and investment into space, complementing public programs and expanding opportunities. The blend of government and private enterprise reflects the enduring influence of the space race, demonstrating how initial rivalry can catalyze sustained progress across multiple sectors. Humanity's aspirations also began to extend toward permanent habitation beyond Earth. Concepts for lunar bases, Martian colonies, and orbital habitats explored the technical, biological, and social challenges of living in space. These efforts drew directly from decades of research on human physiology, life support systems, and space logistics, illustrating the complex value of the knowledge generated since the first beeps of Sputnik. The early space race, in essence, created a chain of technological and scientific advancements that continue to inform planning for humanity's future among the stars. Ethical and philosophical questions persisted as exploration advanced. Issues of planetary protection, resource utilization, and international governance required careful consideration. Policymakers, scientists, and ethicists debated the responsibilities of humanity in uncharted domains, emphasizing the importance of sustainable and responsible exploration. The legacy of the space race thus encompasses not only technological achievement, but also the development of frameworks for managing human activity beyond Earth, ensuring that exploration proceeds with foresight and accountability. Education and inspiration remained central. The space race motivated generations to study science, technology, engineering, and mathematics, producing a workforce capable of sustaining and advancing exploration. Outreach programs, public lectures, and media coverage continued to foster enthusiasm, ensuring that space exploration remained a source of inspiration and a catalyst for human curiosity. The excitement sparked by early competition endured, shaping not only scientific careers, but public imagination and global cultural narratives. By this stage, the space race had become less about political rivalry and more about the collective pursuit of knowledge. International collaboration, technological innovation, and scientific discovery defined the trajectory of human space activity. Governments, private industry, and academic institutions collaborated to address complex challenges, demonstrating the enduring value of the initial investment in capabilities, expertise, and ambition that had characterized the Cold War era. The competition of the past evolved into a shared. As the 21st century unfolded, the vision of humanity reaching further into the solar system became increasingly tangible. Mars, once a distant and enigmatic planet, emerged as a primary target for exploration. Robotic missions, such as NASA's Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance, delivered detailed imagery, chemical analysis, and geological data, transforming the understanding of the planet's history, climate, and potential habitability. Each rover, equipped with sophisticated instruments, traversed the Martian terrain, analyzing soil, searching for organic compounds, and monitoring environmental conditions, laying the groundwork for eventual human presence. These missions were supported by advancements in propulsion, navigation, and communication technology, much of which traced its lineage to the original space race. Autonomous systems, computer vision, and machine learning allowed spacecraft to make real-time decisions, avoiding obstacles and optimizing research paths. Satellite constellations provided constant communication links between Earth and distant probes, ensuring that valuable data reached scientists for analysis. The integration of multiple technologies illustrated how decades of innovation, sparked by Cold War competition, had matured into highly capable exploratory infrastructure. Concurrently, private industry began to play a transformative role in space exploration. Companies like SpaceX, Blue Origin, and Virgin Galactic introduced reusable rockets, dramatically reducing the cost of access to orbit and enabling frequent missions. These private ventures combined commercial objectives with scientific and exploratory ambitions, demonstrating that space activity could be both economically viable and technologically pioneering. The involvement of private enterprise reinvigorated public interest, created new opportunities for collaboration, and introduced market-driven efficiencies into a domain historically dominated by government agencies. The partnership between public and private sectors extended to human spaceflight. NASA's Commercial Crew Program, for example, contracted private companies to develop spacecraft to transport astronauts to the International Space Station, ISS. These programs underscored a paradigm shift. Space exploration was no longer exclusively a symbol of national pride or geopolitical rivalry, but had become a shared enterprise, leveraging the strengths of multiple stakeholders to achieve complex objectives. The legacy of the space race persisted in the infrastructure, knowledge, and organizational capabilities that enabled this evolution. The International Space Station, continuously inhabited since 2000, became a symbol of global cooperation and scientific achievement. Astronauts from diverse nations lived and worked aboard the station, conducting experiments in biology, physics, and earth sciences. These studies provided insights into long-term human health in microgravity, material behavior in space, and environmental monitoring from orbit. The ISS exemplified the collaborative potential first glimpsed during the Apollo-Soyuz test project, demonstrating that space could serve as a platform for shared discovery and diplomacy beyond the confines of political rivalry. As missions extended toward Mars and other planetary bodies, the challenge of sustaining human life became increasingly critical. Research on closed-loop life support systems, radiation shielding, and habitat design sought to ensure astronauts' safety and mission success. Simulated habitats on Earth, including analog environments in deserts and underwater facilities, provided training and data on human performance in isolated and extreme conditions. These programs drew heavily on experience gained from decades of orbital missions, illustrating the continuity of knowledge and the iterative nature of exploration. Ethical and philosophical considerations accompanied these technical challenges. Planetary protection protocols were established to prevent contamination of other worlds with Earth and vice versa, reflecting a growing awareness of humanity's responsibility as explorers. Debates about resource utilization, environmental impact, and governance of extraterrestrial territories highlighted the complexities of expansion beyond Earth. The initial space race, which had focused on symbolic victories and ideological dominance, had evolved into a framework for responsible, sustainable exploration guided by science, ethics, and international cooperation. Simultaneously, Earth observation continued to expand. Satellites provided critical data for climate monitoring, disaster management, agriculture, and urban planning. The ability to track deforestation, ice sheet dynamics, and atmospheric composition offered unprecedented insights into environmental change and informed global policy decisions. These capabilities, derived from technologies developed during the space race, exemplified how the pursuit of space exploration had tangible benefits for life on our home planet, reinforcing the broader significance of investment in science and technology. Cultural and educational impact remained profound. Space exploration inspired literature, films, and media that examined human potential, the search for life, and the meaning of existence in a vast universe. Educational programs capitalized on public fascination, encouraging students to pursue careers in STEM fields and fostering a generation of scientists, engineers, and explorers. The narratives born from the space race continue to shape societal imagination, blending adventure, discovery, and the human drive to transcend limitations. In parallel, advancements in robotics and artificial intelligence enabled more ambitious missions to the outer planets and beyond. Probes such as Voyager, Cassini, and New Horizons transmitted data from regions of the solar system previously unreachable, revealing complex planetary systems, moons, rings, and magnetic fields. These missions extended humanity's observational reach and deepened understanding of planetary formation, atmospheric processes, and potential habitability. The ability to explore remotely with precision and autonomy reflected decades of technological progress catalyzed by the competitive environment of the mid-20th century. The convergence of private enterprise, international cooperation, and advanced robotics set the stage for humanity's next frontier, crewed missions to Mars. Concepts for Martian bases considered challenges of gravity, radiation, life support, and resource utilization. Engineers and scientists modeled habitats, energy systems, and transportation infrastructure, drawing upon orbital experience, robotic mission data, and lessons from analog environments. These planning efforts represent a natural extension of the capabilities and ambition that began during the original space race, demonstrating continuity in human aspiration and ingenuity. Space exploration also prompted reflection on humanity's place in the universe. Observations of Earth from orbit, the study of other worlds, and the quest for life beyond our planet fostered a sense of planetary stewardship and global responsibility. Images of the Earth as a fragile, interconnected system inspired environmental awareness and international dialogue, emphasizing that exploration is not only about discovery but also about understanding and preserving the delicate balance of life on our homeworld. Emerging technologies continued to redefine possibilities. High-resolution telescopes, advanced sensors, and miniaturized spacecraft enabled detailed exploration at lower costs. Swarm robotics, CubeSats, and autonomous systems expanded scientific reach, allowing multiple missions to operate in coordination, gathering comprehensive datasets across diverse environments. These innovations, rooted in the competitive drive of the mid-20th century, exemplify how human curiosity and ingenuity can transform challenges into opportunities for advancement. International space law, governance, and policy frameworks developed alongside technical capabilities. Treaties and agreements, such as the Outer Space Treaty, established principles for peaceful exploration, non-appropriation, and cooperation. These frameworks ensured that as more nations and private entities engaged in space activity, exploration remained conducted responsibly, reflecting a maturation from the rivalry-driven era to a system of shared oversight and accountability. Education, inspiration, and public engagement continued to evolve. Outreach programs, virtual experiences, and global broadcasts of space missions brought the cosmos into classrooms and homes. Students and enthusiasts could follow robotic landers on distant worlds, observe astronauts in orbit, and participate in citizen science projects, reinforcing the enduring influence of the space race on collective imagination and scientific literacy. The vision of human expansion into space became increasingly feasible. Lunar bases, orbital habitats, and Martian colonies are no longer purely speculative. They are grounded in engineering, science, and operational planning derived from decades of experience. Each incremental achievement, from orbital construction to autonomous planetary rovers, represent a step in humanity's long-term journey, a journey initiated by the intense drive, innovation, and ambition that defined the original space race. The convergence of exploration, technology, and culture illustrates the transformative legacy of the space race. While the initial competition was rooted in geopolitical rivalry, its consequences reverberate across science, engineering, education, and society at large. Humanity's ability to reach for the stars, to understand distant worlds, and to apply those insights to life on Earth demonstrates the enduring power of curiosity, determination, and cooperation. As we move further into the 21st century, the space race's influence is unmistakable. The initial rivalry between the United States and the Soviet Union created not only rockets and satellites, but also a culture of innovation and ambition that continues to drive exploration today. Modern space agencies, private companies, and international collaborations all build upon the infrastructure, knowledge, and vision born in the mid-20th century. The legacy of those early decades is evident in every orbital launch, every rover traversing a distant planet, and every human mission beyond our home planet. The technological advancements achieved during the space race have had ripple effects across countless sectors. Satellite communications underpin global telecommunications, internet connectivity, and weather prediction systems. Imaging and remote sensing technologies, initially developed to monitor orbital missions, now track climate change, natural disasters, and urban development. Medical research has benefited from life support innovations and human physiological studies conducted in space. Even material science, computing, and robotics, fields vital to modern industry, owe much to the challenges first addressed by engineers racing to place humanity among the stars. Culturally, the space race reshaped public imagination and educational priorities. Children born during the Apollo era grew up inspired to pursue careers in STEM fields, fueling decades of innovation. Generations of scientists, engineers, and explorers have traced their motivation back to the iconic moments of the 1960s, the launch of Sputnik, the first human in space, and the footsteps on the moon. Popular culture, from science fiction literature to blockbuster films, has mirrored these achievements, embedding space exploration into the collective consciousness and creating narratives that celebrate curiosity, courage, and human ingenuity. International collaboration today reflects lessons learned from the competition of the past. The International Space Station exemplifies how former rivals and new partners can unite for scientific and technological objectives. Multinational crews work side by side, conducting experiments that would be impossible for any single nation to achieve alone. Data from Earth-observing satellites is shared to support climate science, disaster mitigation, and environmental monitoring worldwide. Even as private companies expand their presence, international treaties, ethical frameworks, and shared standards ensure that space remains a domain for peaceful and productive exploration. Looking ahead, the aspirations that began with the Cold War rivalry continue to evolve. Plans for lunar bases, Martian colonies, and missions to asteroids represent not only technical challenges, but also profound social, ethical, and philosophical questions. How will humans adapt to life beyond Earth? What responsibilities do we hold toward other planetary environments? How can exploration serve as a force for unity rather than conflict? These questions remind us that the space race was not simply about national pride or ideological dominance. It was about humanity stepping beyond familiar boundaries to confront the unknown. Robotics and artificial intelligence increasingly extend human capabilities in space. Autonomous rovers explore planetary surfaces, spacecraft navigate independently in deep space, and satellites operate with unprecedented precision. These tools allow humans to expand their reach while mitigating risk, embodying the spirit of ingenuity and problem-solving first exemplified during the space race. International collaboration today reflects lessons learned from the competition of the past. The International Space Station exemplifies how former rivals and new partners can unite for scientific and technological objectives. Multinational crews work side by side, conducting experiments that would be impossible for any single nation to achieve alone. Data from Earth-observing satellites is shared to support climate science, disaster mitigation, and environmental monitoring worldwide. Even as private companies expand their presence, international treaties, ethical frameworks, and shared standards ensure that space remains a domain for peaceful and productive exploration. Looking ahead, the aspirations that began with the Cold War rivalry continue to evolve. Plans for lunar bases, Martian colonies, and missions to asteroids represent not only technical challenges, but also profound social, ethical, and philosophical questions. How will humans adapt to life beyond Earth? What responsibilities do we hold toward other planetary environments? How can exploration serve as a force for unity rather than conflict? These questions remind us that the space race was not simply about national pride or ideological dominance. It was about humanity stepping beyond familiar boundaries to confront the unknown. Robotics and artificial intelligence increasingly extend human capabilities in space. Autonomous rovers explore planetary surfaces, spacecraft navigate independently in deep space, and satellites operate with unprecedented precision. These tools allow humans to expand their reach while mitigating risk, embodying the spirit of ingenuity and problem-solving first exemplified during the space race. Each technological leap demonstrates the cumulative power of decades of research, experimentation, and vision. Private enterprise now complements public missions in ways once unimaginable. Reusable rockets, commercial satellites, space tourism, and cargo missions illustrate a shift from government-only programs to a dynamic ecosystem of stakeholders. Competition remains a driver of innovation, but it is now coupled with collaboration, efficiency, and entrepreneurial vision. The original space race, which began as a contest between superpowers, has become a catalyst for a global movement in exploration and industry. Education continues to be inspired by space exploration. Curricula in physics, engineering, and computer science often reference the historical milestones of the space race. Students engage in hands-on projects, robotics competitions, and coding exercises modeled after the problem-solving demands of space missions. The legacy of ambition, precision, and creativity nurtured during the Cold War continues to empower learners to confront complex challenges, both terrestrial and extraterrestrial. The symbolic impact of the space race endures. Iconic images, Earthrise from Apollo 8, the first human footprint on the moon, astronauts floating in orbit, serve as reminders of what human ingenuity can achieve. These moments transcend politics and ideology, offering universal inspiration. They speak to humanity's collective potential, the courage to explore, and the transformative power of curiosity. Even decades later, they continue to shape how we envision our future, both on Earth and beyond. Scientific knowledge has been the most enduring legacy. Lunar samples, planetary data, and observations of Earth from space have reshaped our understanding of the solar system and the universe. Models of planetary formation, atmospheric dynamics, and orbital mechanics have advanced, informing both theoretical science and practical applications. Space exploration has revealed the fragility of our environment, the interconnectedness of systems, and the importance of stewardship, underscoring that the space race's impact extends far beyond mere technological achievement. Furthermore, the space race demonstrated the power of human collaboration in pursuit of ambitious goals. Engineers, scientists, astronauts, policymakers, and educators worked together to overcome technical challenges and achieve unprecedented milestones. This collaborative spirit is evident today in multinational research projects, international partnerships, and joint missions, illustrating that competition can ignite innovation, but cooperation sustains progress. The evolution from rivalry to collaboration represents a model for tackling global challenges both on Earth and in space. The ongoing exploration of space serves as a testament to human curiosity and resilience. Each mission builds on the lessons, successes, and failures of those that came before. Satellites orbiting Earth continue to provide vital data. Rovers traverse alien landscapes, telescopes reveal galaxies billions of light-years away, and astronauts inhabit stations in orbit, expanding knowledge and capability. The spirit that fueled the original space race persists, driving humanity toward ever greater horizons. In summary, the space race was far more than a competition for national prestige or ideological supremacy. It was a catalyst for technological innovation, scientific discovery, and cultural transformation. The programs initiated by the United States and the Soviet Union, fueled by rivalry and ambition, generated a cascade of advancements that continue to benefit society. They inspired generations, established frameworks for collaboration, and expanded humanity's understanding of the cosmos. From the beeps of Sputnik to the data from Mars rovers, every achievement traces back to a period when nations dared to dream beyond Earth's bounds. The space race reminds us that human ingenuity, when coupled with curiosity and determination, can achieve extraordinary outcomes. It illustrates the interplay between competition and collaboration, ambition and responsibility, imagination and rigorous science. The lessons learned continue to guide exploration, innovation, and ethical considerations in every frontier humanity approaches, whether technological, environmental, or cosmic. Thanks for watching The Other Side Stories. If you enjoyed this journey through history's hidden paths, don't forget to like, subscribe, and share with fellow explorers. Your support helps us bring more forgotten stories to light. Until next time, keep wondering about the past that shapes our future.